In this video, we're going to talk about logarithmic differentiation. We know how to find the derivative of a power of x. So for example, if we're given the function y equals 3x squared, we see that x is in the base of the exponent and we can use the power rule. So for instance, 3x squared, the derivative is 6x. All right. We also know how to deal with the derivative of an exponential function where x is in the exponent. So for example, if we're given the function y equals 3 to the 2x minus 1, we know that we can find the derivative using exponential principles that we've learned in recent videos. We restate the function, and then we multiply by the ln of 3, and then we multiply by the derivative of the exponent. But what do we do if we have a function where x is in the base of the exponent and in the exponent? So for example, the derivative of the function y equals x to the exponent x. Well, if we have a power with x in both the base of the exponent and in the exponent itself, we can determine the derivative by taking the natural logarithm, i.e. the ln of both sides, then using previously learned rules of derivatives such as implicit differentiation and the power rule, among others, to isolate y prime and thus determine the derivative. So let's determine the derivative with respect to x of y equals x to the exponent x. The first thing we're going to do is take the natural logarithm of both sides. So simply write ln y equals ln x to the x. Then recall that we have a rule of logarithms which tells us we can move that exponent in front, right there. Now we're going to differentiate, and you're going to need to use implicit differentiation on the left and the product rule on the right. The derivative of 1 over x with respect to x, the derivative of ln x with respect to x is 1 over x. So the derivative of ln y with respect to x using the chain rule or implicit differentiation is 1 over y dy dx. That'll always be the case. And then the derivative of the right-hand side can be determined using the product rule. We've got x and we've got ln x. The derivative of x is 1 times ln x plus x times the derivative of ln x, and we just said that's equal to 1 over x. So 1 times ln x is clearly equal to ln x, and x times 1 over x is equal to x over x, or in other words, 1. So at the bottom there, we have 1 over y prime equals ln x plus 1. Now, what we can do is simply multiply both sides by y, and that'll give us just y prime on the left, and y times the ln of x plus 1 on the right. And at that point, we say to ourselves, well, we actually have an expression for y. It's literally right there in the question. Y is equal to x to the exponent x. So instead of y times ln x plus 1, we write x to the x times the quantity of ln x plus 1, and that's our derivative. So a similar question here. We're going to follow the same series of steps. We'll take the ln of both sides, so we rewrite the equation, but with ln on the left, ln on the right. And then we recall that we can bring that exponent in front, and our ln y is equal to x to the 4 minus 2x quantity times the ln of the quantity 3x plus 4. Now we're going to determine the derivative on the left. Well, the derivative of ln y with respect to x is 1 over y times dy dx, or as I'm writing it here, 1 over y times y prime. That's something that's worth remembering. It comes up a lot in these questions. The derivative of ln y with respect to x is 1 over y times the derivative of y with respect to x, which I'm calling y prime. That is worthy of a couple of stars at the top. Remember that. So now that we did the derivative on the left-hand side, let's determine the derivative of this portion on the right. In order to do that, we're going to use the product rule. So we've got the derivative of the first times the second plus the first times derivative of the second. Well, the derivative of ln block is 1 over block times the derivative of the block. So the block is 3x plus 4. The derivative of that with respect to x is 3. And so we can clean this up. We can say 3 times x to the 4 minus 2x times 1 all over 3x plus 4. And we have this wonderful expression here. And now we can multiply both sides by y. And when we multiply the left side by y, we'll just have y prime. And when we multiply the right side by y, we re-express it as 3x plus 4 quantity to the x to the 4 minus 2x and multiply by everything that we originally had on the right-hand side in the last line. Okay, moving on to the next question here. Very similar. Y is equal to x squared plus 3 quantity to the exponent x. So what we're going to do is determine the ln of both sides, simply like that. In the next line, bring the x in front, and we have it written that way. Now we determine the derivative of ln y with respect to x, that's 1 over y prime. And then we determine the derivative of the right-hand side. And so to do that, we have the derivative of x times ln of x squared plus 3 plus x times the derivative of the ln of x squared plus 3. And if it hasn't been made clear yet, I'll try to make it clear now. If I have an expression like the ln of x squared plus 3 and I want to know the derivative of that, I go 1 over that expression, and then I multiply that by the derivative of the expression itself. So the derivative of x squared plus 3 is 2x. And that's how we get this right here. Then in the next line, we can multiply the 2x times the x times the 1, and our numerator is 2x squared. Our denominator is x squared plus 3. And now in the last line, we can multiply left side and right side both by y. When we do that, we get y prime on the left, and on the right, we get the original expression for y times the expression on the right that we had a moment ago. Now, sometimes logarithmic differentiation can be used to answer other questions where it might not necessarily be obviously applicable. So we're going to prove the power rule now using logarithmic differentiation, and we're going to do an example where logarithmic differentiation is beneficial to a question that would otherwise be rather complicated. So suppose we have here f of x equals x to the n, and we want to prove that f prime x is equal to nx to the exponent n minus 1. Well, we can do that using logarithmic differentiation, even though on first glance you might be tempted to say, well, wait a second, it doesn't apply here because this is a case for using the power rule. We don't have a variable up there. You might be a little confused for me to say we don't have a variable. Keep in mind that in this example we're giving, the value of n is a constant. We just don't know what it is, as opposed to x, which is varying. So in this instance right here, we would use the power rule under normal circumstances, and we'd say we have nx to the n minus 1. Well, what we're going to do here is use logarithmic differentiation, even though it doesn't necessarily seem to apply. The point being, sometimes you can use it in cases where it doesn't seem to apply to make your solution a bit easier. This is one of those cases. So first thing we're going to do is take the ln of both sides. So given y equals x to the n, we'll say ln y equals ln of x to the n. We'll bring the n in front. We'll say ln y equals n ln x. Now we're going to determine the derivative of the left, which is 1 over y prime. And then we'll determine the derivative of the right, which is just that constant times the derivative of ln x. Every once in a while, a student will say to me, well, why is n times ln x? Why is the derivative of that equal to n times 1 over x? I understand that ln x's derivative is 1 over x, but why is n ln x's derivative n times 1 over x? And the answer is n is just a constant. So just like any other question where there's a constant, you just multiply that constant by the ultimate derivative of the non-constant part. But if it helps you to see it, you could think of it, if you want, as a product rule. So imagine I gave you this expression right here. If you thought of it as a product rule, we'd say derivative of the first. Well, n is a constant which doesn't change, so its derivative is 0, times the second plus the first times derivative of the second. And that's what we said, n times 1 over x. Okay, however you think of it is fine, but we get 1 over y times y prime equals n times 1 over x. Okay, now in our next line, we're going to simply multiply both sides by y. That's a step that we always seem to do here. So we multiply both sides by y, and we plug in for what y is. Y is actually x to the n. It's right up there in the question. So now look at that line here. We've got x to the n times n times 1 over x. We could think of that as x to the exponent negative 1. So we've got this power here and this power here. They have the same base, so we can add the exponents. So that's going to be x to the n minus 1, and then we've got that n multiplying it. So the derivative is actually nx to the n minus 1, which is exactly what we were asked to prove. Suppose we wanted to determine the derivative of this long expression right here. Well, we could do it the old-fashioned way, use the quotient rule. Within the quotient rule, there'd be a product rule up top, and within that, there'd be a chain rule. And it would get a little messy, but it would still work, and you'll get the right answer. But you might say to yourself when it gets complicated enough, I'm going to try logarithmic differentiation. So we just simply say that the ln of the left side is equal to the ln of the right side. And now remember, one of our rules of logarithms tells us that if we've got a times b over c, that's equal to the log of a plus the log of b minus the log of c. Okay? So that would be like saying the ln, because in this case the logarithm that we're dealing with is the natural logarithm. So we'll say the ln of x to the 4 plus 1 plus the ln of root x plus 2 minus the ln of 2x squared plus 2x plus 1. Okay, so we can rephrase that ln of square root of x plus 2 as the ln of x plus 2 quantity to the 1/2. And one of our rules of logarithms tells us we can bring that exponent in front. So we do it and we get that expression right there. So we put that in here. Okay, now what we're going to do is determine each one of these derivatives. Well, the derivative of ln y is 1 over y prime. The derivative of ln x to the 4 plus 1 will be 1 over x to the 4 plus 1 times the derivative of x to the 4 plus 1. And that's what we've written here. We've got that 1/2, so we leave it. And then the derivative of ln x plus 2 is 1 over x plus 2 times the derivative of x plus 2. And the derivative of ln quadratic is 1 over quadratic times derivative of the quadratic. Okay? So we have this expression right here. What we're now going to do is simplify it just a little bit. We're going to take this 4x cubed and multiply it here. We'll have 1 times 1 times 1 all over 2 bracket x plus 2. We'll have 4x plus 2 all over this 2x squared plus 1. So we can simplify, but we can also at the same time multiply both sides by y. And then we can sub back in for what y actually is. That's given in the question. Y is actually equal to this expression. So we plug that in here. And we have this lengthy expression for y prime. Now, at x equals, it's supposed to say negative 1 here. At x equals negative 1, we're going to plug that in. And we're going to go through a series of steps for evaluating. And again, there should be a negative 1 right there. And after going through all those steps of evaluating, we get that dy over dx is equal to 1. Okay? And finally, our last example, we're going to use logarithmic differentiation. We're going to be given a logarithmic function in a base other than e. So it'll be log, but it won't be ln. And we're going to see that in these cases, we convert our logarithmic equation to the equivalent exponential equation. Then we'll use the natural logarithm. So, for instance, suppose we were given this equation right here. We have a straightforward example of y equaling logarithm to some base of an expression. The very first thing we're going to do is the first thing you learned about logarithms. you learned that you can express this equation as 3 to the exponent y equals the argument of the logarithm. That's vital for you to be able to do in a question like this. So, like we say, we do that right away. Now, we're going to take the natural logarithm of both sides, and then we're going to bring the exponent in front of the ln. We've seen this move a lot. We bring that y in front, and we get this. And now, in a moment, we're going to multiply both sides by 1 over ln 3. If I multiply y times ln 3 times 1 over ln 3, I get y. And if we multiply ln of that quadratic times 1 over ln 3, we get literally 1 over ln 3 times the ln of that quadratic. Now, you might be thinking to yourself, okay, we've isolated y. That's good. I like the fact that we've isolated y. But gosh, it's isolated in the original equation. Why would we go through all this work just to isolate it again? The reason is because the derivative of ln is so easy to do. That's why. See, we don't like this log base 3 because that derivative is not easy to do. But log base e, that derivative is, we have a formula for that, a method. That's why we did it. We want to get it in there. And we've got this little constant in front, 1 over ln 3. No big deal. We just leave it there. It's not hurting anybody. If you're curious, ln 3 is roughly 1.09. 1 over ln 3 is roughly 0.91. It's like saying y is equal to roughly 0.91 times the ln of that expression. That 0.91 is not hurting anybody. Okay, so we show that step here, multiply each side by 1 over ln 3, and we get this expression. And now, one more time, if it helps you to see it this way, it's totally not necessary, but you can see this as a product rule. We've got 1 over ln 3, which is the constant roughly equal to 0.91. And we've also got the ln of that quadratic. Well, we could do the product rule. Derivative of the first, well, the derivative of a constant is 0, times the second, which is the ln of that quadratic, plus the first, which is 1 over the ln of 3, times the derivative of that quadratic, which is 1 over the quadratic, times derivative of the quadratic. Now, this 0 times the ln of 4x squared minus 5x plus 1 cancels out, and this is what we get as the derivative on the right side, which is what we're showing here. Now, you don't have to go through all of that thinking. Just remember, if you have a constant times a function, the derivative of that will be the constant times the derivative of that function. Okay, so you can then put that all together as one numerator, and you'll get 8x minus 5 times the ln of 3 over 4x squared minus 5x plus 1.